Hello, my name is Grace Fanson, and I am an undergraduate physics student here at Georgia Tech, and I have recently started a research project on the Arabia Terra region of Mars with Dr. Rivera Hernandez and with Dr. Ray. First, I'll give you a little background on the existing research, and then I'll tell you about my specific project, including my objectives, methodology, and results. So, 70% of Mars's surface has been resurfaced by volcanic activity, which can't be accounted for by the existing volcanoes, or the volcanoes we already know about. This has inspired a search for other sources of this volcanic material, and we are starting to consider other sources. On Earth, we have something called a collapsed volcano, like Crater Lake in Oregon, which you see in the top picture there. Crater Lake used to be a high elevation volcano and has since fallen to around the same elevation as the surrounding land. If it exists on Mars, if it exists on Earth, it could exist on Mars too. And there have been some proposed collapsed volcanoes in the Arabia Terra region of Mars. For some context, here is a topographical map of Mars with the Arabia Terra region circled. Zooming in, we can see the Terra, which is a bowl-shaped depression on a planetary surface called Eden Terra. It's the #1 candidate for a collapsed volcano, and I'll talk a little bit more about this particular Terra. It was once thought of as an impact crater, although it doesn't have a lot of the characteristics of an impact crater, like near circular geometry, a central peak, and raised rim. So these factors have contributed to the hypothesis that this might have been a volcano in the past. My project is to test this hypothesis to look into the mineralogy of the surrounding area. There are some minerals that are indicative of altered volcanic material, and they include silica, glass, smectites, zeolites, and sulfates. Each element and mineral has its own spectral signature, and an instrument called XRISM aboard the Mars Reconnaissance Orbiter can record these spectra, and I can look at them to try to determine what minerals are on Mars. Going back to Eden Terra, we can look at this map, which includes all of these little bow tie shapes, which are XRISM images. The first thought would be to look at Eden Terra to determine its mineralogy, but unfortunately, we don't have any XRISM images on Eden Terra. However, if Eden Terra was a volcano once, there may be minerals in the surrounding area. The crater I have circled is 200 kilometers away from Eden Terra. This is an existing model showing the thickness of the volcanic deposits as a function of distance, and Eden Terra is labeled there. And the thickest deposits are within 500 kilometers from the Terra. So the data I'm looking at should be within that range, and if there are volcanic materials, I should be able to find them using the available XRISM data. This is that image I had circled in the crater nearby Eden Terra. The process is to use something called a parameter, which is essentially a filter that takes out parts of the light spectrum that don't have indicative spectral features of a particular mineral. This is an example of one of those parameters. This creates a kind of heat map where you can find minerals, and this parameter helps us find silica. So the bright spots should show us silica. Now you might notice there are these big stripes running north and south across the image, and that is a result of how XRISM takes data. Essentially, it starts at a shallow angle and takes a panorama of the land below, which is why we have kind of this bow tie shape. And different parts of the sensor are more sensitive to different kinds of light. So we will see some streaking down the entire image. It's unlikely we have silica channels running north and south across a crater, so we have to take that into consideration. What's more likely is if we have bright spots going across multiple parts of the sensor, and if they also correspond with the geology below. This part of the image corresponds with the crater's rim. The next step is to recombine all of this data and create a spectrum. And here is the spectrum from that particular region of interest. You can see absorption lines at 1.9 and 2.2 microns in my data on the left, and on your right is the example spectrum from the CRISM team of hydrated silica, and you can see those same 1.9 and 2.2 absorption lines. So this is a vote of confidence for silica in the area. Another way to use CRISM data is to create color images by assigning different parameters, different colors in an RGB image. This introduces another level of nuance, so you can see multiple minerals in some areas. And as you can see here, there might be aluminum smectite in the yellow areas. And I say might because you have to look at the spectrum, otherwise you don't know for sure. These are essentially guesses based on the software. So I took another region of interest in a very similar location. You can see it's right next to the first region of interest, and I created another spectrum. And this time, we also have an absorption at 2.3 microns. And this is actually consistent with magnesium or iron smectite. The software might have guessed aluminum smectite because of the 2.2 micron absorption line, which we know might have actually been silica. So in this case, we may have more than one mineral in the area, which is why we have this particular spectrum. Both of these minerals are consistent with volcanic activity on Mars. There is a lot more data to be analyzed, and I'm going to spend a lot of time looking at other CRISM images, as well as potentially doing a thermal analysis of the area to determine if the thermal signatures of the area are consistent with volcanic material. So there may be volcanoes. It remains to be seen, and more work will be done. Thank you very much. Oh, does anyone have questions?
All right, thank you, Grace. We have plenty of time for questions, so if anybody has questions, feel free.
Are there any hypotheses as to why those minerals are on the edge of that crater, or if they were, deposited from volcanism nearby and then might have been stored in the edge for any particular reason?
Sure. So, actually, related to this is, if you imagine there was a volcano, there might be volcanic material covering the entire surface. And so you might wonder why this whole image isn't just bright with silica. And the reason is because these volcanoes existed a really long time ago, and there's a lot of Martian dust covering everything. And that's why we only get little peaks. And so if there is an outcropping of silica, especially on the rim of a crater, it may be because that particular part of the crater doesn't have as much dust. And I think that's why I am also a little new. So there may be other contributing reasons, but I think that's one of them.
Any other questions?
Thank you. Is the CRISM instrument still working on the spacecraft?
No, I don't believe it is. I mean, I think it is mostly done taking data, I think.
Which explains why we can't get direct data from the crater.
Yeah.
Okay. Thank you.
Any other questions? Okay. If not, thank you so much, Grace.